All right, we are going to talk about the introduction of algebra combined with trig. And it might be a little bit scary, but what we're going to do first is we're going to do some practice with the algebraic, because we're going to do the left-hand column here. All right, we're going to do some distributive properties. So in order to do this, we're going to expand x plus y times x plus y. And that's going to give us x squared plus 2xy plus y squared if you were to multiply it out. And then we're going to factor the difference of squares here, which is going to equal x plus y times x minus y. And then we're going to factor a trinomial, which is all this is algebra 2 stuff that we've done before. And that's going to be x and x, the factors of x squared. And then we need the factors of 4 that might add up to 3. And it's going to be a 4 and a 1. And this has got to be negative and plus because the inner product and the outer product have to sum to a negative 3. All right, and then we're going to add two fractions together. And we have to find a common denominator here. And in this case, it would be 1 plus x times x. And then I have to multiply this first fraction by 1 plus x because 1 plus x over 1 plus x because it doesn't, I'm sorry, I try again. I have to multiply this first fraction by x over x because it doesn't have this denominator, and I'm going to get x squared. And what do I mean by that? I mean that we're going to multiply this one by x over x, and this one by 1 plus x over 1 plus x, so that we have a common denominator. And I'm going to get x squared for the contribution from this first term, and then we're going to get 1 plus x quantity squared, which I'll have to expand. So we get x squared plus 1 plus 2x plus x squared all over 1 plus x times x. And then we're going to get 2x squared plus 2x plus 1, if I put it in the exponents in decreasing order, and times over 1 plus x quantity times x. All right, so we just found a common denominator and found a fraction, a single fraction out of 2. Now on this one, we're going to rationalize using the conjugate, so we don't have a square root in the bottom, and we're going to multiply it by our favored factor of 1, which would be 1 minus root 2 over 1 minus root 2. And we do that because the numerator will stay the same, but I have now introduced the factors here of a difference of squares. So I'm going to go 1 squared minus root 2 squared, which is 1 minus root 2 squared is 2. And this is going to equal 1 minus root 2 over negative 1. And if I distribute the negative 1, we get negative 1 plus root 2. All right, so all that's familiar algebra that we've done in the past. With a variable, well, what a variable is just a placeholder for a value, some number. And if we think about it, we could do some algebra with trig, because sine of x is just a placeholder for the ratio of the opposite over the hypotenuse, which is just a number. And the cosine is a placeholder for the adjacent over the hypotenuse, which is also just a number. So we can treat the entirety of sine x and the entirety of cosine x like it's a variable. All right, and so we can expand this just like we expanded this over here, and we can say that it's sine x plus cosine x times sine x plus cosine x. All right, and then we can multiply sine times sine, which is sine x quantity squared. But when we square a trig function, we put the 2 in between the n and the x. That's math convention, so that we show that we're squaring the sine and not just the x. Okay, and then I can multiply my inner product and my outer product, and I get sine times cosine and sine times cosine, which means I'm going to get 2 sine x cosine x plus cosine squared x. And there we have a similar outcome, except instead of variables x and y, we're using variables that are going to be sine x and cosine x, which are representatives for just a number. Okay, and then now we're going to factor the difference of squares here, just like we did here. And then we'll get sine x plus cosine x times sine x minus cosine x. And we just factored the difference of squares using trig functions. Again, similarly, instead of using the variable x here, we're going to use tangent as our variable and work this into two binomials here. So what are the factors of tan squared x? Well, that's just tan x and tan x. And then the factors of 4 that might add to 3, we'll just say 4 and 1 again. And the inner product and the outer product have to sum to -3. So this has to be a -4 and this has to be a +1. So the only difference you see here is that instead of an x, I'm using the entirety of a tan x, which is representative of the opposite over adjacent, which is a number, just like x would be a placeholder for. All right. This next one, I'm going to be obviously doing the same operation here. I'm going to find a common denominator here. So let's do that. Common denominator will be 1 plus sine x times cosine x. And then I multiply this first fraction by cosine x over cosine x because that's the part of the denominator this one doesn't have. And then I'm going to get a cosine squared x on top plus, I'm going to multiply this one by 1 plus sine x over 1 plus sine x because I don't have that part of the denominator in this fraction. So this will be 1 plus sine x quantity squared, and we're going to expand it just like we expanded this one. And that means we're going to get cosine squared x plus 1 plus 2 sine x plus sine squared x all over 1 plus sine x times cosine x. All right, so we've done algebra with trig functions. And now we're going to use the conjugate with trig function. Now the conjugate here was 1 with 1 plus root 2, which turned out to be 1 minus root 2. And we're going to do the same favorable factor idea, except we're going to say 1 plus cosine x over 1 plus cosine x. That's a factor of 1. It's not changing this value at all. It's just changing the way it looks. And then I'm going to distribute, and we get sine x times 1 plus cosine x all over 1 minus cosine squared x. And now we have multiplied times the conjugate and got something that looks a little bit different. All right. Now you might think, well, why would we do this? Well, because we have fun and exciting equations to solve that involve trig functions, which is really cool. All right. Now, we're going to learn about something called identities. And we've learned about one of them already. And I'm going to start with the Pythagorean identity, the one that we have talked about before. A Pythagorean identity implies that we're talking about a right triangle. And if you recall, if I had a unit circle, here's my unit circle, and I have a radius of 1, and I have an angle of rotation theta. And what is this point right here on the unit circle? Well, it's just cosine of theta, comma sine of theta. All right, and if I were to create a right triangle out of that, I'm going to blow this right triangle up a little bit so we can see it better. This is the right triangle that we see. And this is 1, and we said that this point was cosine theta, sine theta. Well, the distance that I traveled over here to get to this point is cosine theta. So this leg's distance or length is cosine theta, and this leg's distance or length is sine theta. And using Pythagoras, I can square the two legs, sum them together, and I will get the hypotenuse. So this first Pythagorean identity is going to be cosine squared theta plus sine squared theta, although I'm going to use x here because all of my other problems are using x. So it doesn't matter if your variable is x or theta for your angles. So we'll just use x. And then it's sine squared x equals 1. Now I like to call this one the big one. Because we're on the hunt for the big one. Because that always helps us sometimes when we're solving equations, when we see it. Okay? So that's the big one. Well, as you can see, there are 2 more spots for Pythagorean identities. But I could take the big one, which is cosine squared x plus sine squared x equals 1. And I could, using this right here, I could solve for sine squared x. Or I could solve for cosine squared x. But we're going to talk about that in a minute. But what if I decided to do this? What if I divided the big one by, I should say dividing by, cosine squared x. Let's say I took the big one and divided by cosine squared x, which would give me cosine squared x over cosine squared x plus sine squared x over cosine squared x equals 1 over cosine squared x. Okay, now cosine squared over cosine squared is just 1 plus, and then sine squared over cosine squared, well, sine x over cosine x is tangent, so this would be tangent squared x equals secant squared x. So this is our second identity here. So 1 plus tangent squared x equals secant squared x. And I got that by dividing the big one, the big equation here, by cosine squared. So what could I do similarly? I could divide the big equation, the big one, by sine squared. And what would we get? We'd get cosine squared x divided by sine squared x plus sine squared x over sine squared x equals 1 over sine squared x. All right, well, cosine over sine is not tangent, it's cotangent. So this would be cotangent squared x plus sine squared over sine squared, which is 1, equals, well, 1 over sine squared is going to be cosecant squared x. And this is the third Pythagorean identity, which would be cotangent squared x plus 1 equals cosecant squared x. So we have 3 Pythagorean identities. Now, what do we mean by the word identity? That means wherever I see cosine squared x plus sine squared x, I can replace it with a 1. They have the same value. They have the same identity. And the same thing here with 1 plus tangent squared x equals secant squared x. Wherever I see a 1 plus tangent squared x, I can replace it in my equation with a secant squared x. And cotangent squared x plus 1 equals cosecant squared. I could do the same thing here. Okay, now, so 1 is a really cool number to be able to replace something more complicated with. So let's talk about some reciprocal identities. Now, what do I mean by that? I mean each trig function that we talked about before has a reciprocal. And when you multiply a number by its reciprocal, you get 1. So if I were going to multiply sine x by its reciprocal, which would be, I heard it in the back there. Yeah, okay, I heard it. It was cosecant x, because cosecant x is equal to 1 over sine x, and when you multiply something by its reciprocal, you get 1. All right, what about cosine x? Well, if you were to multiply it by its reciprocal function, which would be secant x, you're going to get 1. And then if I were to multiply tangent x by its reciprocal function, which is cotangent of x, you get 1. So these are nice identities to know, because if you ever see these two multiplied together, you can replace them with a 1. All right. Now let's get back to the big one, which is cosine squared x plus sine squared x equals 1. And what if we decided to take this equation and solve for sine squared? Well, in order to solve this equation for sine squared, I would subtract cosine squared from both sides and get 1 minus cosine squared x. And then if I solved it for cosine squared x, it would be 1 minus sine squared x. Now, you might say that replacing sine squared with something where subtraction is more complicated, but guess what? This factors. This is the difference of squares, and so is this. And so sometimes it's important for us to have something in our equations that will cancel. So these can be really helpful from time to time. All right. Now, what if I took the other Pythagorean, the second Pythagorean identity, 1 plus tangent squared x equals secant squared x, and I took that identity and I solved it for tangent squared? Well, what would I do? I would subtract 1 from both sides, and I would get secant squared x minus 1. And then what if I solve for the 1? I wanted to get 1 all by itself because we like to have things that equal 1. Well, what would we do? We would take secant squared x and we'd subtract tan squared x, and we would get another identity which is equal to 1. All powerful stuff in trig here. All right, what about cotangent squared x plus 1 equals cosecant squared x? Well, cotangent squared x, if I were to solve this equation for this, would be nothing more than cosecant squared x minus 1. And if I were to solve this equation for 1, we would get cosecant squared x minus cotangent squared x, and we'd also get 1. All of these four factor because they're the difference of perfect squares, which is really kind of neat. So this right here, this page, is going to be one of the most important pages for this whole semester. So this one's an important one. We'll keep this close to us so that we can keep referring back to it. All right. Okay. We have another set of identities called the cofunction identities, which look a little bit like shifts of functions, but I want you to consider, if you will, the right triangle. I'm going to draw a right triangle. Here we go. Here's a right triangle. And I'm going to make this my right angle, obviously. And I'm going to name this angle theta. And if I name this angle theta, if I'm in radians, this would be pi over 2 or 90 degrees. This angle here, up in the upper left corner here, would be pi over 2 minus theta. Okay, and remembering this is 90 degrees and this is 90 minus theta. That's the same thing in degrees if it helps. Okay, now these two angles are complementary because they sum up to 90 degrees. Complementary because they sum up to 90 degrees. And so I'm just going to label this one C, this angle C, and we'll call this one A and this one B. And let's say I wanted the sine of angle pi over 2 minus theta. Well, if I were to do that, this is opposite side here is little a, this is little b, this is little c. But so the sine of an angle, and this would be my angle choice here, would be the opposite, which is a over c. Well, is there another angle that has that same ratio, or another trig function or trig ratio that has that same a over c? Well, if I have a over c, that could be the adjacent to this one. So I could say cosine of theta is equal to a over c. And do you see how they're equal? So I'm going to say this is cosine of theta. Okay. And this works because they're complementary angles. Okay. Complementary cofunction identities. All right. Now, what happens if I want to find the cosine of pi over 2 minus theta? Well, if I want the cosine of pi over 2 minus theta, that would be b over c. And then what if I tried to find another angular or trig function that would give me a b over c? Well, if I chose this theta and did the opposite over, so I could say that sine theta equals b over c. And do you see how those are the same? So this is going to equal sine theta. And like I said, this works because they're complementary angles to each other. And think about the sine of 60 is equal to the cosine of 30, and vice versa on our unit circle that we've been studying. All right, so the tangent of pi over 2 minus theta, so the tangent here would be the opposite, a over b, and then that would be equal to the cotangent of theta because that's its complementary, and then the cotangent would be tangent of theta. The tangent here, let's go over it just to make sure we're sure of it. Tangent of pi over 2 minus theta is equal to a over b. Well, what would the cotangent of theta be? Cotangent is going to be the adjacent over the opposite because it's the reciprocal of it. So it's going to be a over b. And then similarly, if you flip the angles, you'd get tangent theta. And if you were a betting person, secant of pi over 2 minus theta, and its complementary would be cosecant here of theta, and this one is going to be secant of theta. All right, and all of this works again because these are complementary angles. All right, so these are good identities to know from time to time as well. Not as important, I would say, as these, so we're not going to forget these. All right, next one. Odd and even identities. Okay, so let's review what it means for a function to be odd. Remember, back in the day in Honors Algebra 2, you guys would do f of, or Algebra 2, f of negative x equals negative f of x. And for even, you would say f of negative x is equal to f of x. Okay, and graphically, this is reflected over, the odd functions are reflected over the origin. And the even functions were reflected over the y-axis. Okay, now I like to think of, if I were doing an angle of rotation here, let's say I have theta equals, or we'll try x here because we're using x here. Let's say x equals pi over 4. What is its opposite angle? Well, its opposite angle would be x equals negative pi over 4. And what is this point here? It would be a root 2 over 2, comma root 2 over 2. I chose pi over 4 because most of people like pi over 4. And this point in quadrant 4 would then be root 2 over 2, negative root 2 over 2. All right, now, let's say my angle is pi over 4. What would the sine of the opposite of pi over 4? So the opposite of that would be negative pi over 4. So the sine of negative pi over 4, what does that equal? That equals, well, you come to negative pi over 4 down here with our angle of rotation. That's what? Negative root 2 over 2. And what does that equal? Well, that equals the opposite, because the sine of pi over 4 is equal to root 2 over 2. So I would say that the sine of negative pi over 4 is equal to the opposite of the sine of pi over 4, making the sine function what? Odd. So we would say that this is equal to negative sine of x. So it's odd. Now, if I looked at a graph, I happen to have Desmos open here, and I graphed y equals sine of x. And that's the graph of all the y values. Do you see how it is reflected over the origin here? So do you see how the sine function is indeed odd? Okay, because most people have a better time seeing that. All right, so let's go back to our discussion here. Nice. Okay. It keeps wanting to pop up. Great. Lovely. We'll just make it really small since it's being annoying right now. Okay, and I'll move this over. All right. So what about the cosine? If I were to do the cosine of negative pi over 4, does that equal the cosine of positive pi over 4? Yes, so this one would be equal to the cosine of x, which means this is even. All right, now let's open this annoying thing again, and let's hide this one, and we'll look at the graph of all the x values on the unit circle. Do you see how this one is reflected over the y-axis? So this one isn't definitely even. Let's see if it stays closed. It doesn't stay closed. So I'm just going to move it over here. All right. Tangent of negative x. Now tangent, I'm positive and positive in quadrant 1, and in quadrant 4 I am positive and negative if I'm a point in those quadrants. Now tangent is the y over dx. So this is tangent is positive in quadrant 1 and tangent is negative in quadrant 4. So this one is going to be the opposite tangent of x. So this one is odd. The tangent of pi over 4 is 1. The tangent of negative pi over 4 is negative 1. And so they are opposites. And if we were to graph it, I'll bring my naughty Chrome back here since it's not behaving. And we'll say y equals tangent x. And if we were to graph that, do you see how this is symmetrical with respect to the origin and is also odd? And this is a graph of all the tangent functions. All right. Okay. And interestingly enough, if you think about it, tangent is sine x over cosine x. And since sine is odd, the odd takes over in whether it's even or odd. Okay. Now, cosecant is 1 over the sine. So this is going to be also odd. Because if you think about it, this is 1 over sine of negative x, and that would equal 1 over negative sine of x. And so this one is also odd. So cosecant is odd. Secant, now I should show you the graph of that too. The graph of all of the cosecants, let's see, that's y equals cosecant of x. I know it's an interesting graph, which we will just we will discuss graphing trig functions in the next unit. But I just wanted to give you a look at this as being odd reflected over the origin here. Okay. All right. Next one. I'll just leave it open. It wants to be on top. It wants to dominate this screen. All right. Secant is the reciprocal of cosine, so it's going to follow the cosine, and then this one will also be even. So this is secant of x. So the reciprocal of an even function is even. And then cotangent is going to be odd as well because it is going to be cosine over the odd function of sine. So that makes this one also odd. Okay, and if we were to look at the graph of, let's look at secant to be consistent. You'll see that secant is reflected over the y-axis here very nicely. And then lastly, I didn't graph cotangent. So this is y equals cotangent of x. And this is negative down here, positive up here. Do you see how it's reflected over the origin? This one's a little harder to see sometimes, but anyway, they are indeed reflected over the origin here. All right, so cotangent's also odd. All right, so goodness, our list of identities is expanding. We've got these identities. We're not going to forget these. These are really important ones. Then we have the reciprocal ones, the Pythagorean ones, and the other ones that we derived from the Pythagorean identities, as well as the complementary ones, the cofunction ones, and the odd-even identities. So wherever you see sine of negative x, you can put negative sine of x. Wherever you see cosine of negative x, you can put cosine of x because it's even. So we're going to work a whole bunch of examples to show you how to solve some problems with these, like right now. All right. So use identities to find the value of the expression. All right. Well, I know that cosine of theta equals 0.34. Okay, so I've got to think of a way to find this expression. So I'm going to say cosine of theta. I'm going to start with this. And then I'm going to look at my list of identities here. And the ones that I'm thinking we're going to use has a cofunction idea with it. Well, here's my cofunction list. And the one that's closest is this one. So I know that cosine theta equals this. So I can make that change right away. I can make this identity help. So I'm going to say the next line is going to be sine of pi over 2 minus theta is equal to this. But that's not exactly what this is it? It's close, except what I need to do is factor out a negative. And if I do that, I get theta minus pi over 2 because the signs flip when I factor out a negative. And now sine of a negative value of an angle, pulling out my other one here, is odd. So I can pull out the negative. I can say that this is equal to negative sine of theta minus pi over 2, and I'm closer. And I know that this is 0.34, 0.34, 0.34. Okay? And I want to solve for this. So I'm going to divide by -1, and I get the sine of theta minus pi over 2 is equal to negative 0.34. And there's my answer. So I had identities help me transform my equation into something that I knew I had to get to. So it took me a couple of steps to get there, but I used my identities list to help me out. All right, what about this next one? I've got the tangent of pi over 2 minus theta equals negative 5.32, and I want to find the cotangent. Well, this one's a really simple one because if I go to my cotangent identity page, what is tangent of, my cofunction identities page, the tangent of pi over 2 minus theta is equal to cotangent. So I can make a straight up substitution here. Cotangent of theta equals negative 5.32 because tangent of pi over 2 minus theta is equal to cotangent. And I'm done. I should have done this one first, right? This one's easier than this one. I should have done this one first, but hindsight is 20/20. All right. So what we're going to do now is we're going to use our basic identities to simplify an expression. That means I'm going to make it simpler than what I started with. For example, I am multiplying here by 2 trig functions. It'd be nice if I ended up with something that wasn't multiplication. Well, sine of pi over 2 minus y. Now I can use y as my angle measure, but that's okay. I can use y, x, theta, gamma, alpha, beta, all sorts of letters, variables I can use for my angle. And this looks like I can right away change sine of pi over 2 minus y to cosine of y. Now, why might I want to do that? Because if I go back to page one of the most important pages, I know that my reciprocal identities here, if I multiply secant times cosine, I'm going to get something really wonderful. Right? I get a number 1 because secant times cosine, they are reciprocals of each other, and you multiply them, you get 1. All right. Next one, let's see. I've got to simplify this one. Now, I look for things that I can change, okay? Sine I can't really change, but I can change cotangent into something. Well, if you recall, cotangent is equal to cosine over sine, and I can make this sine of u over 1. And then I can cancel these factors out, and I get cosine of u, which is a much simpler expression than multiplying two trig functions. This is simpler. Okay. Now, before I go on to ones that are more complicated, I want to take us back to page 1 of our notes. You know, the page where we did our algebra of trig, and see if we can simplify our expressions. Okay? I want you to be on the hunt for things that make your life easier. Like we're looking for the big 1. Do you see that here? Well, you've got a cosine squared and a sine squared, and you're adding them together. So what does that equal? Well, this equals a 1. So we can say that this is equal to 1 plus 2 sine x cosine x. And this is a simpler expression than the one we started with. This one here we can't really simplify. And this one here we can't really simplify. But let's see if we can find any other versions of 1. If you look at the numerator here, do you see anything? Do you see that this is cosine squared plus sine squared? So cosine squared x plus sine squared x equals 1. So we can change that to 1 plus 1, which is 2, plus 2 sine x on top over 1 plus sine x times cosine x. Now you'll notice I'm not multiplying the denominator out because I know something nice is going to happen. I can then factor out a 2, and I'm running into this problem here, so I'm going a little bit to the right here. And I get 1 plus sine x over 1 plus sine x times cosine x. And since I have factors here, I can cancel these 2 out, and I'm left with 2 over cosine x. But 2 over cosine is even simpler when I express it like 2 secant x, because 1 over cosine is equal to secant. So all of this madness here, where I'm adding 2 fractions that are a lot more complicated, using my trig identities, I can break it down and simplify it into a single trig function, which is really nice. Okay? Now, this last one right here, I have sine x times 1 plus cosine x. And I have in the denominator 1 minus cosine squared x. Well, where have I seen this before? Well, if I took the big one and I solved it for sine squared, I see that sine squared x equals 1 minus cosine squared x. So I can replace the denominator with, I can say sine x times 1 plus cosine x over sine squared x, because I can replace the denominator, this 1 minus cosine squared x is equal to sine squared x. And then this is now a factor. I can get rid of one of these, and I'm left with 1 plus cosine x over sine x. And then I could bust up the fraction and say 1 over sine x plus cosine x over sine x. And 1 over sine x is equal to, you're right, it's equal to cosecant x plus, and then cosine x over sine x is equal to cotangent x. So this expression right here is even simpler than a fractional expression of sine and cosine. So you can see how these trig identities can make expressions that are a whole lot more complicated simpler. So let's go about it. Let's do some more. Let's practice some more. All right, so, wow, we're going to simplify this one. Well, guess what? We just saw this one. What did we say this was equal to? 1 minus cosine squared x is equal to, remember, pull this, our favorite sheet out, is equal to sine squared x. Now, why am I happy to see that? Well, because sine squared theta over sine theta, I can replace this and I can get rid of one of these and I'm left with the expression sine theta, which is a lot simpler than 1 minus cosine squared theta over sine theta. All right, this next one. All right, let's see if we can find something wonderful in this one. What do you see in the numerator? Well, I see a sine squared u and a cosine squared u. So we know that that's going to equal 1. So we can say we have 1 plus tan squared u now over secant u. Now, 1 plus tan squared u equals something because it's one of our Pythagorean identities here. 1 plus tangent squared x is equal to secant squared x. So I can change this numerator to secant squared u over secant u. And I can get rid of one of the secants on top and cancel out the bottom one, and I'm left with secant u. And this expression is simpler than the one we started with. A whole bunch less letters in that one, huh? So what happens is that once you have these trig identities memorized, you start seeing what you might need to do to make your expressions simpler. All right, let's see. Let's do another one. All right. Now, visually, I'm looking at these two and I'm thinking, well, this might have something to do with even and oddness because I have a negative x in here. Well, recall, cosine is an even function and so is secant. So I can just say that secant x and cosine x go here because they're even. I can drop the negatives. I'm not really drop the negatives, but I don't need the negative. They're equivalent without the negative. And these are now reciprocals of each other. So this whole expression simplifies to 1 because these are reciprocals of each other. Okay. Now, secant, this is secant of negative x squared minus tangent of x quantity squared. Now, this is an even function, so I can drop the negative. So I can say that this is secant squared of regular x minus tangent squared of regular x. And that we've seen before in our identity sheet here. If you solved for 1 using the other form of the Pythagorean identity, secant squared x minus tan squared x is 1. So that is, of course, simpler than what we started with up here for f. Okay, moving right along. Another example. All right. Now, we're going to simplify this expression to either a constant or a basic trig function. That means it's going to be a sine, a cosine, a tangent, or, a singular trig expression. Okay? The other interesting thing about these is that there's more than one way to go with these identities. You could go many different directions and can still get the same answer. So there's not necessarily just one path to the solution. Okay, now I'm not going to lie, this number 4a is pretty challenging. But what do you notice right away? Well, I noticed that we have different trig functions here, which is kind of annoying. But I know that tangent x and cotangent x are both composed of sines and cosines. Okay, so what I'm thinking I would do is I would change this to 1 plus sine x over cosine x over 1 plus cosine x over sine x. And this is where the algebra gets a little bit complicated, but it's not impossible. I'm going to find a common denominator in the numerator, which would be cosine. So here's my common denominator in the numerator. And I have to multiply the 1 by cosine over cosine. So this is cosine x plus sine x, because this one already has a denominator. And then this denominator needs a common denominator, which I'm going to say is sine x. And I'm going to multiply this 1 by sine x over sine x, which is going to be sine x. Plus, this one doesn't have to be multiplied by anything because it already has a denominator. And now I have a double-decker set of fractions here. And I'm going to keep the numerator. Here it is, cosine x plus sine x over the denominator, which is cosine x, times, and I'm going to flip the denominator. So this is sine x over sine x plus cosine x. Now, this is addition. So cosine x plus sine x is the same thing as sine x plus cosine x. So these are factors, and I can cancel these, and I'm left with sine x over cosine x. And that's just tangent of x. Okay. Now, some people might multiply this by the conjugate of the denominator. You could do that too. And I have done that in the past. And I will show you the answer doing it that way, where you multiply by the conjugate of the denominator, and then you get 1 minus cotangent squared x in the bottom. And then eventually you have to change them to sines and the cosines to get the tangent. So you can do it this way. It just takes a few more steps to get there. And the math sometimes might be a little bit more complicated. So if they're the same, if they're the tangent and the cotangent up here and they're mixed, I usually change things to sines and cosines and it falls out pretty quickly. All right, this next one. Let's see, what can we do? Well, seeing this is a clue because that's a cofunction identity. And what is the tangent of pi over 2 minus x equal? Well, let's go back. I got to find my sheet over here. The tangent of pi over 2 minus x is equal to the cotangent of x. All right, so we're going to change that. So this is the cotangent of x times the cosecant of x all over cosecant squared x. All right, I can reduce this by a factor. This is can get rid of one of these, and I have one of these, and I'm left with cotangent of x over cosecant of x. And now I think I'm going to change things to their sines and cosines component parts. So cotangent is cosine x over sine x divided by 1 over sine x. And if I keep the numerator, cosine x over sine x, multiply and flip the denominator, I get sine x over 1. And these sine x's cancel now because they're factors, and I'm left with cosine x. Boom. And I have my one singular trig function out of all of this. Okay, so what did I do? I looked at this and I said, well, that's a cofunction identity. I know. So the cofunction identity for tangent is its cotangent because they're complementary. And so that's cotangent of x. And then I knew I could cancel one of these out. And then I changed things to sines and cosines, and that fell right on out. Okay? All right, let's do some more. Practice makes you better. All right, number 5 says use the basic identities to change the expression to one involving sines, only sines and cosines. then simplify to a basic trig function. Okay, well, sine theta you can't really change. Tangent I can change to sine theta over cosine theta times cosine theta. This is really over 1. Plus, well, the cofunction identity for cosine of pi over 2 minus theta is sine of theta. Okay, and then these two cancel, and I'm left with sine theta minus sine theta plus sine theta, which gives me just 1 sine theta. And so there's my simplified expression. Tricky, but we did it. All right. Now here we go. I'm looking at this, and what do I see right away? Well, these look like factors of the difference of squares, right? So I can say that this is secant, oops, can I spell? I can say that this is secant squared y minus tangent squared y all over secant y. And I'm looking at this going, maybe something wonderful will happen. Let's see. If I go back to my very important page and I have my identity 1 plus tan squared x equals secant squared x, what do I see? I see that secant squared x minus tan squared x equals 1. So something wonderful happened. This is 1 over secant y. And 1 over secant, well, that's just cosine of y. That's not too scary. Now, we could have changed the secant and the tangent and all of these into sines and cosines. And if we did that, this is what it would look like. And you'll see that you'll get the same answer. It just takes longer to get there. Okay, so if I were to change the secant to 1 over cosine minus sine over cosine, because that's what tangent is, times 1 over cosine plus sine over cosine. And this is over 1 over cosine. Since they're all over the same denominator, if I multiplied by cosine y over cosine, if I multiplied by cosine y over cosine y, what happens to all the denominators? Well, they just cancel out. Okay? But let's say I didn't do that, and since these have the same denominator, I can say that this is 1 minus sine squared over cosine squared y times cosine y, and the cosines will cancel because this is cosine squared y over cosine squared y equals 1, and I'm just left with my lonely old cosine y. So I probably would not have done it this way because it takes more steps. Not that it's not possible to do it this way, it just takes a couple more steps. This way is definitely, I think, the easier way to go because we're on the hunt for things that equal 1. All right. All right, let's do another one. All right. Secant squared x times cosecant, secant squared x plus cosecant squared x on the bottom. Now, if you look at the big 1 identities here, you'll notice that the tangent's only with the secant squared, and the cotangent's only with this cosecant squared. So the fact that these are different is not helpful. Okay, so I'm thinking we're going to change things to their sine and cosine component parts because if all else fails, you can do that. So let's see what we get here. In the numerator, we get 1 over cosine squared x, and then this is 1 over sine x, all over, this is going to be 1 over cosine squared x plus 1 over sine squared x. And the numerator is going to look like cosine squared x sine x in the bottom. And now I'm going to find a common denominator in the denominator, which would be cosine squared x sine squared x. And then I'm going to multiply this first one by sine squared x. And this one by cosine squared x or cosine squared x, which gives you cosine squared x. And what do we see? We see something wonderful just happened. this right here is equal to 1. So I can say that this is equal to 1 over cosine squared x sine x over 1 over cosine squared x sine squared x. And I can keep the numerator using my algebra of fractions here, 1 over cosine squared x sine x times cosine squared x sine squared x all over 1, and I can cancel out some factors here. Well, cosine squared and cosine squared cancels, and I can get rid of this sine squared and one of these, and I'm left with simple, lonely old sine x all by itself, which is what the directions wanted us to do. Okay? Now, the visual clue here of what I have to do if I have two fractions I'm adding together, that means I have to find a common denominator. All right, so that's going to be easily enough. 1 minus cosine x times sine x. And I'm going to multiply this fraction by the sine x over sine x because I don't have that part of the denominator. And I'm going to get sine squared x. Plus, this would be 1 minus cosine x quantity squared because I have to multiply this one by 1 minus cosine x over 1 minus cosine x to get that same denominator. And then I'm going to expand this, which means I'm going to get sine squared x plus 1 minus cosine x times 1 minus cosine x all over 1 minus cosine x times sine x. Now, it's really tempting here to want to cancel out this 1 minus cosine and this 1 minus cosine, but we can't do that because these aren't factors I'm adding here. They're not just pure factors. So I have to do some work up here. So let's see what we got. We got sine squared x plus 1 minus 2 cosine x, if I were to multiply this out, plus cosine squared x all over 1 minus cosine x times sine x. And hopefully you're getting a little bit better at noticing some things. And do you see a sine squared x and a cosine squared x up here? And what does that equal when you're adding them together? All at once? 1. Yes, something wonderful just happened. So these two things equal 1, and 1 plus 1 is 2. So we get 2 minus 2 cosine x all over 1 minus cosine x times sine x. And I'm noticing that I can factor a 2 out of this numerator, and I get 2 times 1 minus cosine x over 1 minus cosine x times sine x. And now these are factors, and I can cancel those because they're factors, and I get 2 over sine x. But 1 over sine x is cosecant, so this is 2 cosecant x. And so the craziness of adding two fractions that have trig functions in them simplifies all the way down to 2 cosecant x. So what was the visual clue on how to simplify this? Well, since we had two fractions, we had to find a common denominator. And then we expanded the binomial here, squared, and notice that we got a 1. And then we could factor something out and then cancel something in the bottom, and it falls out from there. All right, let's do some more. Practice makes it better. All right, so number 6 says, write an expression in factored form as an algebraic expression of a single trig function. Okay, so we're going to factor this. Looks like something we could factor. So let's try it. Well, what are the factors of 1? Well, it's 1 and 1. And then what are the factors of sine squared x? Well, that's going to be sine x and sine x. And then my inner product and my outer product have to sum to -2, so both of these are negative. And I get 1 minus sine x quantity squared. And this is an expression in factored form in a single trig function. So that works. Well, this one's a little bit more complicated. I got to get a single trig function. But I know that I can replace the squareds by something. I can't replace sine x by anything, but I can replace cosine squared x with something. We can replace cosine squared x with 1 minus sine squared. So I'm going to replace that. So we're going to, where we see sine x here, minus 1 minus sine squared x, because cosine squared x equals 1 minus sine squared x, minus 1. Now you'll notice when I substitute in, I'm using parentheses here because I have to distribute this pesky negative. All right, so this will be sine x minus 1 plus sine squared x minus 1. So then I'm going to put them in descending exponent order. So this will be sine squared x plus sine x minus 2. And now we have to factor. Let's see here. We get sine x. The factors of sine squared x are going to be sine x and sine x. The factors of 2 are easy. It's 2 and 1. And the inner product and the outer product have to sum to a positive 1 sign. So this will be a plus 2 sine x and a minus 1 sine x gives me a positive sine x, and 2 times negative 1 is negative 2. So there you go. There's factored form in a single trigonometric function. So if you have different trig functions, you have to replace the squared term with an equivalent that has the same trig function as the unsquared term. Okay? More practice. All right, we're going to do the same thing here. I could change the sine squared, but I'm going to hold off and figure out what this equals here in the middle. So I'm going to say sine squared x plus, well, what is 1 over cosecant x? You're right. It's sine x plus 1. Good. And then I'm going to factor. Sine squared's factors are sine x and sine x. And the factors of 1 are 1 and 1. And the inner product and the outer product have to sum to 2. So they're both plus. So this will be sine x plus 1 quantity squared. And there you go. All right, so I'm going to factor this one. This is the difference of squares. So what's being squared here? Well, 2 cosine x. So I can say 2 cosine x plus 1 and 2 cosine x minus 1. And that's as simple as the difference of squares. Okay? So factoring is kind of fun with trig functions. It's the same, it's just you've got more letters to write. All right, here we go. Now, why would we do this? Well, because we need to be able to solve equations. I gotta make sure my calculator's close. All right, so I'm going to solve for all solutions. Now we'll worry about all solutions in just a minute, but when is the cosine positive? I need a calculator because this is not one of the standard values that I know. So this process is the same. The cosine is positive in quadrants 1 and 4, excuse me. So I'm going to have a quadrant 1 solution and a quadrant 4 solution. Okay, but I don't know what alpha is. I got to find out what alpha is. And that's going to be the inverse cosine of 0.75. Now this doesn't state whether we're going to use degrees or radians, but let's stick with radians. Okay. All right, so I'm going to turn my calculator on. And I am in radian mode, which is really, really nice. So I'm going to clear this out. So I'm going to go second inverse cosine of 0.75. And that's going to give me alpha, which is 0.723. We'll use 3 decimal places for now. Okay. Now, in my first quadrant, I know that x will be 0.723. Okay, but I could hit that multiple times going around. So how would I get all of the ones that happened in the first quadrant? Well, that would be plus every time I go around is 2 pi n, an element of the integer set. That would be x1. x2 would be 2 pi minus alpha, right? Because I went all the way around and I'm alpha short. So what would that be? That would be 2 pi minus, I'm going to grab my number here, and that's 5.560 plus 2 pi n and an element of the integer set. Okay, or see, I could say plus or minus, I could say x equals plus or minus 0.723 plus 2 pi n and ez and an element of the integer set, because this would be the plus angle and this would be the minus angle. So I could do one statement with both answers. Okay. All right, so we just found every solution going around infinitely many times using our nice integer set notation. All right, what about the tangent? Well, the tangent is positive in quadrants 1 and 3. So I'm going to have a first quadrant solution and a third quadrant solution, but I don't know alpha for this case. So we're going to go alpha is inverse tangent of 5. Getting our calculator out here. Second inverse tangent of 5. And we get alpha equals 1.373. And so x is going to equal, well, the first quadrant solution is just going to equal alpha, so it'll be 1.373 plus. Now, in this class, we're just going to add pi and 2 pi to our solutions to get our solutions to the trig equations here. So how far is the next solution? How far away is it? Well, if I were to add pi, I would get to the, because pi is 180 degrees, right? If I were to add pi, I would get the next solution, wouldn't I? And if I took and added pi to that solution, I would get the next solution. So I can say plus pi n here and an element of the integer set, and I hit them all by just adding pi n every time, okay? Yep, and we're doing radians here. All right. So that's just a refresher on how we would solve in one go round, but then we can also do as many, infinitely many go rounds as we want. All right, what about sine squared x equals 0.4? Well, I'm going to take the square root of both sides here. So we're going to get sine x equals plus or minus the square root of 0.4. Well, what is the square root of 0.4? If you don't know, second square root 0.4. You would think it would be, so we check our answer, we square it, right? And get 0.4. You would think it'd be 0.2, but it's not, so be careful. So this is sine x equals plus or minus 0.632 roughly, right? Well, where's the sign plus and minus? Well, the sign is plus and minus in all the quadrants, positive and negative in all the quadrants. So we got to get them all covered here. All right, but that's an alpha I don't know. And remember, alpha is a positive first quadrant angle. So we're going to go the inverse sine of, and I'm just going to go so that I get the most accurate answer. I'm going to go second inverse sine of square root, second square root 0.4, and close. And we're going to get 0.68. It helps if I put a point. 0.685. We round to 3 decimal places. All right. So now I'm going to challenge us here to answer in one statement here. If I say 0.685, which would be the first quadrant solution here, how far to the next solution? It would be pi, right? And if I added pi, I'd get another solution. I'd add another pi, get another solution, get another solution, so on. So I could say plus pi n for one of mine. But what if I said plus or minus? Does that cover? Let's see, this would be the minus solution, minus 0.685. If I add pi to it, I get a solution, add another pi, get another solution, add another pi, get another solution, and so on. So this covers all of them. If I do plus or minus 0.685 plus pi n. Okay. All right. Now I love to do one like this because we don't have a secant button inverse secant button on our calculator. So we are going to use the reciprocal function of secant, which we do have in our calculator, which is cosine. So what's the reciprocal of secant? Well, it's just cosine x. So that means I have to take the reciprocal of the other side. Okay. There we go. Now cosine is negative, and I just leave it like this. Cosine is negative in what quadrants? Well, that's 2 and 3. So I'm probably going to have a positive solution and a negative solution here. If I'm finding all of the, now remembering this is pi. Okay, but I don't know what alpha is. So alpha is going to be the inverse cosine of, watch it now, because it has to be of the positive, because alpha is a positive first quadrant angle, 1 over 5.32. I just leave it like that. All right, so let's see what we get when you do that. Inverse cosine of 1 divided by, well, we can use our little fractional thing, can't we? I forget that we can do that. I can go alpha F1 and get my numerator over my denominator and get 1 divided by 5.32, and we get 1.382, right? And this solution can be plus or minus, because the plus, this is alpha. So my first solution is going to be plus or minus pi minus alpha plus 2 pi n and an element of the integer set, because I'd have to go all the way around to hit it again. But what is pi minus alpha? Well, that's easy enough to calculate. We're going to go second pi minus, grab this one and subtract, and we get 1.60. Wait, 1.760. Whoops, I should say my plus or minus. Plus or minus 1.760 plus 2 pi n and an element of the integer set. Now let's see if this works, our solution. Remembering that this is pi over 2 up here, which is 1.57 approximately. So 1.76 is definitely a second quadrant angle in radians. So the positive, and to hit it again, I'd have to go around 2 pi. So the positive 1.760 plus 2 pi n hits every one of them in the second quadrant here. And then the negative 1.760 plus 2 pi n every time will get me all the negative ones. So that works. Okay? So that's it. I went over. Let's summarize really quickly. Introducing the algebra of trig, which means we can factor, we can expand, we can find common denominators, and we can use the conjugates, both with algebra and trig. And if we use it with trig, we'll simplify our expressions. We also learned about the reciprocal identities, where if you multiply two trig functions, you get 1. Those are really nice ones. Then we learned about the big one, which is what we generated from the unit circle. Cosine squared plus sine squared x equals 1. And then we divided the big one by cosine squared to get the second Pythagorean identity. And then we divided the big one by sine squared to get the third trig identity, Pythagorean identity. And then we manipulated each one of those Pythagorean identities to get some other interesting ones that we can use when we are going to be solving our equations. We also talked about the cofunction identities, which apply because sine and cosine are the same when you're using complementary angles, and same with tangent and cotangent, which is really kind of cool because that's a nice little substitution that you can do to solve some problems. And then we also talked about the even and oddness of sine, cosine, tangent, cotangent, and secant and cosecant. And so it's going to be in your best interest to have that memorized, the cofunction identities memorized, And we'll use them so much, they'll become second nature to you. But that's all I have as an introduction to the algebra of trig and simplifying some trig equations and refreshing our memory on solving some basic trig equations. All right, well, so thank you for your kind attention, and we will see you next time.